It was delivered last year, and we measure during the daylight, and as Caroline says, it's because we're seeing backscattered sunlight and getting the fingerprints of the molecules out of that. And one important thing that we'll sort of emphasize later, again, is that we are the first of these 8 or 10 satellites that was specifically designed to measure ozone in the lowest atmosphere where we have to breathe it. It's been a real challenge, but it's a challenge that we've overcome. So, this is Joe. He's our administrator with the season tickets to the Patriots, and so Joe is at geostationary orbit. So he's 22,000 miles away from the Earth over the equator, and looking at to where the center of our measurements will be, so our field of regard. The other satellites that have gone up are at much lower orbits, so they're in usually about an eighth of Earth diameter away, and they'll sort of go around like that, and they usually measure one place on Earth, each place on Earth, every day or so, or sometimes less. And because they're looking at so much territory, and we're concentrating on North America, the size of the piece of the ground they measure at a time is much, much larger. And so, it happens to be very close to my my grandparents' farm, where we would end up many summers, but it wasn't really chosen for that reason. So the reason we're in geostationary, and what geostationary is that the satellite appears to be stationary over the equator. And the reason for that is that the higher you go above the Earth in an orbit, the longer it takes to go around. So if you go high enough, 22,000 miles, then it will take your satellite 24 hours to go around the Earth. But meanwhile, the Earth is turning every 24 hours. So if you get them lined up in the right direction, it will be apparently stationary. And you know, if when you see people with satellite dishes getting TV, they're looking at one of these things, and they're looking up because of where they are on the Earth, and mostly south, because in the U.S. we might be looking at one of those, and they don't have to rotate around every 24 hours either. So we'll be here, 93 West, which is just about at the Texas-Louisiana border, only south to the equator. And yeah, so where we are now, we've been building, it's built, it's completed, accepted by the government and delivered, and it's in storage, and we will launch it, as we said, in early 22. We're kind of an experiment in that NASA is going to put us on a commercial geostationary satellite host rather than buying our own satellite, which is a forward-looking solution to do interesting science measurements from space at lower cost. So here it is. It goes from there down to there, and that's the carriage they move it around with. So you can get a size of the scale. So this is in the clean room. I tried to go into the clean room once, and by the time I got half of that stuff all on, I was feeling so claustrophobic I had to quit. Because they really, I mean, working in that stuff for hours at a time is quite amazing. So the instrument concept I won't dwell on a lot. It's a fairly ordinary type of spectrometer by now. And we've been working on it for many, many years. And we're looking in the ultraviolet and visible. We'll see that in a little more detail in a minute. And it's fairly ordinary sort of spectral resolution, but very sensitive. The field of regard you'll see again, and you'll see how we sweep. You saw it when we were coming in. I had that picture moving. And at the center of the field of regard, near my grandparents' farm, the size of the ground pixel is about 2 kilometers north-south and 5 east-west, so 10 square kilometers. And then we'll sometimes have to clear away because of clouds and not look there. And then here are our products. And first of all is, I'm saying is the ozone, where we're looking close to the Earth, which we call the planetary boundary layer. And we call the technique XL ozone because XL are Shang Liu's initials, and he's the one who has made it work so brilliantly. Here are the other things we were measuring. We'll get to see what their importance is a little bit later, and that's the nominal spatial resolution again. Now, the science questions. It's a little hard for me here. So it's built to answer 6 basic science questions, and they are, first of all, mapping out where the emissions that are responsible for bad air quality come from. So gases and aerosols, and the worst things for us are ozone down here and aerosols down here, especially the finer particle aerosols that can really get into your lungs. And then we need to look at the processes that transform things into ozone or aerosols and how they're transported from where they're made to where they go. The link between climate and air quality is something we also look at. So there are 3 basic problems in atmospheric measurements. The ozone layer that you've all heard about, air pollution that we're talking about, and climate forcing and having to do with global warming. So it turns out that climate forcing affects air quality more than air quality affects climate forcing, but they're still important to look at the relationships. Number 4 is how can we improve air quality forecasts and assessments? And this is why we work, for example, closely with the Environmental Protection Agency and NOAA, so that they will be able to use our data in their modeling and forecasting. Intercontinental transport, both by us to Europe and especially by Asia to us, is an important source of pollution, particularly for us. There are times when places on the west coast of the U.S. cannot meet their required levels of pollution, particularly for ozone, because they're not making it, it's coming in from Asia. And then the last of these are episodic events. So fires are terrible pollution sources. And they go far downstream of where the actual fires are. Dust outbreaks, volcanic eruptions, all things that affect air quality that are episodic, so that we will want to look at closely and very quickly after they happen. So you can't have a good science instrument without a strong science team. So that's, I guess that's me and Shang and Caroline and maybe Gonzalo. But in fact, we go much further than that. So we have, I'm not going to read all the names, but these are the U.S. Members of the science team and people who are actually working on the data analysis algorithms with us are in bold. And then we have the foreign science team, so very strong Canadian and Mexican science teams. And we have a building Cuban science team. It's hard to work with Cuba. It's not easy to go there. It's not easy for them to come here, but they will get all of the data. And then we have strong collaborations with ESA and the Dutch and I mentioned Cuba already. Oh, and the Koreans, because they're doing the third leg of this stool. So that's a bit about the team, and you also have to have a team be well organized, right? So here's the organization chart, right? So that's me and there, and those are the other. Now this is another one of those eye charts, but what I wanted to point out here is that NASA had a multi-year study of what you would want to measure from geostationary orbit. Half of it was for air pollution, the other half was for ocean science. So we're doing the air pollution, and in the air pollution, two of our colleagues in particular led this wonderful study. So Daniel Jacob from Harvard here and Doreen Neal from NASA did all the herding of cats and made this chart that goes from the science questions to what you want to measure. So we'll just zero in a little bit on it. So measurements of gases, and so these are the kinds of things that, or these are the things that we want to measure. These are the things that tempo will measure. Carbon monoxide, methane, ammonia, you have to measure in the infrared, and so we can't do it from tempo, but others will be doing it. And this last one is the height of the aerosol plume, which we can't measure by ourselves, but we're flying together, not as one satellite, but at the same time with the NOAA weather satellites, and combining those data, we should be able to do a pretty decent job of that. So here's what we measure. So a little bit of spectroscopy. So this is in nanometers, right? And so the visible starts here at about 380 nanometers and goes up to about 740. And this is starting the near infrared, and below there is ultraviolet. So up top, we're measuring the sun. This is an artifact of the instrument that will divide out when we divide the Earth by the sun. This is measuring the Earth, and see all these structures are the fingerprints of our molecules. And then here I've taken their ratio and gotten what the albedo or reflectance spectrum looks like. And we all know and love all of these little wiggles in the spectra, of course. I picked 4 spectra from the GOM-1 satellite, which is the first one that we were working with. And since we're at an observatory, there are a lot of people who are very interested in extrasolar planets and who's going to find the first Earth-like one. And, and we have one. So this is what clouds look like. So they're bright and they're white. This is a desert scene. So that bump in the desert scene explains why deserts are hot during the day and cold at night, because it can absorb all of this radiation and get hot, and then it can re-radiate it and get cold. Vegetation looks like this. This is the famous vegetation red edge, and this is absorption by chlorophyll, and if you see that little bump there, that's the minimum in the chlorophyll absorption. And then the ocean is, it's dark and it's blue. I keep wanting to use this to change because I'm not used to this. This is just to show you a little bit about what some of the wiggles that we're interested in are like. And I'm not going to go through in much detail, but I will say that we've been able to fit down to about this level in a logarithmic scale, which means we're doing very, very well indeed. Now, I wanted to explain why we're doing this stuff at the Smithsonian instead of studying dinosaurs or feeding the lions or that kind of stuff, because we are the same Smithsonian. Well, one of my scientific heroes is Samuel P. Langley, who became the secretary of the Smithsonian in 1890, at which time he established the Smithsonian Astrophysical Observatory, which spent its first 65 years in Washington, in back of the castle on the mall where the nice garden is now. And then we came up here. He had to invent all of his own equipment. The bolometer is a a famous type of detector used in these studies, so he invented it. He needed to record spectra, so he designed and built his own chart recorder and techniques for analyzing spectra. And this in particular I want to show you. This is from 1900, so it's the first volume of the Annals of us. And Langley and Abbott, who later became secretary of the Smithsonian, developed some analysis techniques for spectra using photographic techniques in the 1890s, and then were sort of rediscovered by some of our European friends in the 1970s, now that they had computers to work with. Okay, so I'm going to diverge from tempo a bit to show you what we've done in the past that leads us up to being able to do this now. So now with the low Earth orbiting satellites, we've been able to measure everything that we need to measure for air pollution, except for that XL ozone, which we have now developed. Starting in 1985, when we got into this business, and making the measurements when the first GOM satellite measured in 1995. So these, especially these molecules here, are things that go through processes of oxidation and give you ozone in the end, or in some cases give you fine aerosol particles that you don't want to breathe in the end. So this is some of the spectrometers that we worked with in the past, and I'm not going to read it, but I just did want to point out that we're over 10 billion measurements of spectra from space and counting. So we've had a bit of experience. And here's some of the experience. So, NO2 is a pernicious pollutant, and the Los Angeles area is a particularly good example of it. This is from Chong, and here he's showing the stratospheric ozone in the red, which is the ozone layer which we want, and then the ozone down below near us, which we don't want. And this happens to be at a time when there's an ozone hole. So the red should, this is the south polar region, the red should go all the way there, but it doesn't because we have an ozone hole. Helen Wang and our group has done a wonderful job in developing a water product, and I just want to digress a bit on why that's important. You can do a lot of things with water measurements, and we have one of the finer ways of doing it now. Some methods can do land and not ocean, or ocean and not land, and we can do well on all of them, which lets us look at things like atmospheric rivers. Atmospheric rivers are a fairly hot topic in our field these days. You've probably, or some of you have probably heard of the Pineapple Express, which is when it really gets going, from the direction of Hawaii, it can carry more water in the atmosphere than the Amazon River, and it can dump it on California. So we'll get prior knowledge of a lot of that. And another thing that, it's a strange one, but happens to be a particularly interesting one to me, is if you go to the Midwest, and you go during corn season, so it's hot, you're growing corn, you have to give it water. Corn does a lot of evapotranspiration. So a field of corn is just like a fire hose shooting water vapor into the air. So you can get this huge dome of water vapor in the air, and then if it drifts, say, over Chicago, it can raise the heat index for Chicago by up to 9 degrees Fahrenheit, which turns a real hot spell into a disaster. Here's SO2 from Kilauea and volcanic fog in Hawaii, which I've experienced, and it's very unpleasant. You get this very fine pumice that will get right into your pores and takes days to get out, and it's also not good to breathe it. we pioneered measuring formaldehyde from space, and that's important because it's the main proxy for the volatile organic compounds, which are an ozone and aerosol source. We also did drawing a blank, Caroline. Glyoxal, sure. Also glyoxal, so here's an example of that. And in fact, the Guangzhou area of China always lights up because that's where China's chemical industry is, and paint factories and all that stuff are. So those are some snapshots. This is from Shang. It is a movie of tropospheric ozone over a number of years, done with the GOMS satellite. NO2, whenever you see a pretty picture of pollution, it's usually NO2 because it's easy to measure, the sources are local, so you get these hot spots standing out. So here's over Europe, and you see the Po Valley here in Italy, and you see all the industrial parts and the agricultural intense stuff in Germany and the Netherlands. And we switch, we go to the Middle East. So this is all the oil stuff there along the Gulf. And that is the Nile Valley and Cairo and the Nile Delta. Now, China is pretty bad, Japan can be pretty bad, but if you want to take a vacation somewhere where the air is fresh and clean, then you could go here. Because there's very little industry, very little pollution, unless it comes in from China. And then us, of course, again, and we already pointed out that LA is a major issue. Here's for formaldehyde, and when trees, especially certain types of trees, get stressed by heat, then they put off isoprene, which gets oxidized through a pathway that includes formaldehyde, which we can measure. So it's the main proxy for volatile organics. And the reason it's there is that, so this is in summertime, and you sort of have trees on the left to right side and hot on the bottom. So that's sort of the product of hot and trees, and with the isoprene coming out and us measuring it as formaldehyde. Here are some more global maps that we've done. So this is also a summertime, and you see what we just showed you, but you also see burning in the Amazon and burning in sub-Saharan Africa, the Chinese paint factory. And then a different type of year, it moves around. So this is more the biological source in South America now. And the agricultural burning moves from down there up to here in Africa. And China always stays lit up. This is the same with glyoxal. We can pick out a couple of forest fires here in the Northwest and in Siberia, and of course the Chinese paint factory. And then at a different type of year. I showed this before, so I don't need to really spend time on it. I did want to show this one, though. Volcanoes put out a lot of sulfur dioxide. They also put out a lot of ash that can be really damaging to aviation, for example, because volcanic ash melts at just about the temperature that jet engines like to run, so it's easy to lose engines. So here Caroline has taken SO2 from the volcano Mount Kasatochi and has shown not only how much SO2 there is, and therefore a good measurement of how much ash might be there, but also how high in the air it is. So it's up there 9-10 kilometers. So that was a very nice analysis. So now we're going to go back to tempo. That gives you, I hope, a little background on where we're coming from. Here are our measurements again, and here is the XL ozone, and then the others that we've seen several times, and some numbers that probably won't mean much to you, but they happen to be very good numbers indeed. And here is what we will do every hour during the daylight. So we measure from Puerto Rico down here up to Hispaniola in Cuba and the Bahamas, most of Mexico, that's Mexico City, most of Canada up to the Athabascan oil sands and Atlantic to Pacific. Now, but suppose we had a forest fire here that we wanted to study more intensely, or some other phenomenon, a volcano in Mexico. We can sacrifice the measurement time for coverage. So, for example, we could look at the western sixth of this. The north-south is fixed. The western sixth of that we could look at 10-minute resolution, for example, to see, what a forest fire is doing in almost real time. And then here is how the size of the pixel changes with location. So when Joe's looking out at the globe at the center of the field of regard, where it gets more curved up above, it gets worse, and when it's closer to the equator, it gets better. So in Mexico City, we're at 8 square kilometers, and even up at the oil sands, we're at 21. We can even see up to bits of Alaska, but we don't really know how useful that's going to be just yet. Now here's some more concrete examples. So LA area, we'll measure that every hour. Here's a grid for Puerto Rico, and we'll do that every hour. Here's a comparison of tempo, 4 of our measurements with some of the older satellites, the OMI satellite. There's one of theirs and one of Gomes. And, so we're quite high resolution compared to previous instruments. And why do we want to measure so often during the day? Well, things vary during the day, and Jack Fishman, who's on our team, produced this some years ago, showing how the NO2 varies during the daytime. The yellow blocks are daytimes and these are nights. But one of the satellites, the OMI satellite, for example, will only measure once a day here and there, and that's when the amount is the least. And it gets interesting at other times. So these dots are 1 hour apart, so we would do sort of that. Oh, here are 2 measurements from an airplane that is helping out with tempo and the data analysis by Caroline. The same day over the Denver area, showing how things can change between morning and afternoon, and giving you an idea of what another reason why you have to measure at higher spatial resolution, because it's higher temporal resolution, because they move around a lot as well. Here is the composite, the constellation. So we do North America. Our colleagues at European Space Agency do Europe, and our colleagues in Korea do Asia. And it would be very nice to have 3 more of these, because they really need one in South America, especially what's been going on with the burning in the Amazon. There's huge amounts of pollution in Africa, but it's very much under-measured. So having one there would do us a ton of good. And then the third one would fit nicely over the Middle East. So hopefully someone will take that on. Now, how am I doing for time? Okay. I wanted to divide, okay, we have this paper out. This is the other website to look at. And it officially got published this week. And these are many, many members of the Tempo science team and our collaborators. And we go into all of these kind of measurements that we want to do as projects and as experiments in some cases. So I've divided them up into the normal time resolution studies, which means every daylight hour, and the things that we might want to do at higher time resolution. And I won't do all of them, but I've picked out some of them. So air quality and health is our main job. We will have a measurement of ultraviolet exposure using algorithm developed by our colleagues at NASA and the Finns. We'll have advanced aerosol products that can do a much better job of looking at especially the small aerosols that get way, way down into your lungs. And we'll do that by combining tempo data with the NOAA weather satellite data, which measures much farther into the infrared. We'll look at pollution specifically for oil and gas fields. The other satellite we're involved in will do that for methane as well. And I mentioned the water vapor studies. So those are automatic. And over time, pollutant inventories. We certainly look at transport of pollutions regionally and locally, and transboundary, like the pollution from Asia coming to the West Coast. Now, at high time resolution, lightning produces a lot of nitrogen oxides, and they will produce ozone. So how much is produced that way is hard to study, but we can look at areas that are predicted to be stormy, and those can be quite robust in certain parts of the country in the summer, and measure at high time resolution over the storms and in the outflow regions, and see what we're getting. And if we think about, say, rush hour, we want to see what's happening when cities wake up and go to sleep. Air quality responses to sudden changes in emissions. Well, that could be could be a fire. And there's a lot we don't know about whether it's more polluted under a cloud or when there's no cloud. And that's something we could have a look at. And agriculture is something that we're really trying to do something with, because most of what you're doing when you fertilize your farm is trying to put nitrogen in for the plants, plus a few other things, right? But if you put your fertilizer on at the wrong time, then you're wasting it from your plants, but you're also polluting the atmosphere. So we'll do studies of agricultural soil on nitrogen. For example, after rainstorms hit, and if that does something to elevate the amount of stuff that comes off, which we've seen it do with the other satellites in certain locations. Okay, so scientists do what we call drinking from the fire hose. These satellites put out huge, huge amounts of information, and not everyone wants all of that. Your state or regional or local people in charge of pollution, or even the weather people, might want limited amounts of it. And there are tools, and I've picked out one of my favorites, the EPA's Remote Sensing Information Gateway, that will take all of this data and let you say, well, I don't want all of that. I want over here from this time to that time, and on this resolution grid and in this format. So I can just go in after a couple hours of training and do that. 5 more?
15 if you want it.
Oh, okay, good. I have a couple of things that I didn't know how far I would be by this time, because every time I practiced it came out different. So air quality and health. So that's a main thing of ours, and we'll look at air quality on short time scales at high spatial resolution. So that's very, very useful. Working with the EPA and with NOAA, we'll improve the air quality indices and directly supply things so that you can, say, look on your smart device and see if you can go for a run this morning. Experimental opportunities, this is more for the scientists, but we can spend up to 25% of our observing time looking at the non-standard things. So trading spatial coverage for time resolution. And I mentioned that we will see events, and I mentioned several experiments, and the Tempo Science team and many other people have come up with great ideas for that, and that's all in that paper that I mentioned right there, a bit back. I mentioned traffic, so morning and after high-frequency scans. In fact, if we start when it's light on the East Coast, it's still dark on the West Coast. So one of our IT guys has come up with a wonderful method of sort of, instead of just scanning over and being in the dark, of doing this kind of a thing so that we creep across at higher resolution until it gets light on the West Coast. And then as the day goes on, we sort of repeat that on the West when it's dark in the East. And we'll do just concentrated studies, because that doesn't help for Chicago, but we'll do concentrated studies of important urban regions as well. Biomass burning is a big deal with us because of the huge amount of pollution that fires pump out. And there's still a big unknown about how much ozone comes out from particular fires. And so we'll have this suite of molecules and the aerosols to really, we hope, dope that out in great detail. And we have a group of 6 or 8 people on the science team and also collaborators who are really interested in looking at the fires in greater detail. One of our team, and this is Jim Carr, who is the guy who is in charge of the pointing for the NOAA weather satellites, and I go like that because they take the whole disk of our side of the Earth every few minutes at much higher spatial resolution and much more accurate pointing than we could ever hope to do. In fact, we borrow our pointing from them. But he figured out that we could do a pretty nice job on looking at city lights. So you can do it very precisely with this instrument that's in orbit with NOAA right now, but it's only one single band. You're not looking at a spectrum. So you can see where the light is, but you can't tell what kind of light it's coming from. And so since we're looking here and here, but at very high spectral resolution, we can distinguish among these different light types. Okay, a few more. So lightning knocks I mentioned. So we'll do that for thunderstorms. It's coupled slightly with soil knocks. Our colleague Liat Yegley from University of Washington years ago worked with us to see the stuff coming off of the soil. And the first example was the Sahel Desert. At the end of the dry season, when the rain first hit, you got just large amounts of this stuff coming up. And in recent years, she and other colleagues have really done world inventories of how much of this stuff is coming out. But we'll do it on much finer timescales for North America. I mentioned the croplands. And in fact, these all work together, sort of coupled. Doing better on soil lets you do better on lightning and vice versa. And also the soil and the croplands. This is my last slide without going into backups. Our colleagues at NASA Goddard Space Flight Center are doing a lot of development of using these kind of spectra for vegetation products. So Joanna Joyner is leading the effort there for us. So soil-induced fluorescence lets you look at primary productivity both on the land and in certain kinds of stuff in the ocean, like detecting red tides. She also has interest in estimating soil pigment contents and concentrations. And I mentioned the UV briefly, but that's also a collaboration with NASA and with Finland. And with that, I think I've come to the end of my talk. Thank you very much. But I figured that this would be enough.
All right. Do we, do you have a microphone? Are you going to walk around? Okay. So I guess thanks, Kelly, a lot for that talk. Now we can have any questions? Yes? Oh, do you want to bring the mic?
So you mentioned the desire to have more satellites aloft. How much does it cost now that you know how to build it? How much does it cost to add an additional satellite?
If you partnered with a communication satellite, like say Elon Musk wanted to do Africa and he wanted to do the partnering, then it would be probably in the 250 to 300 million range. If you wanted to have your own satellite, like the Koreans do, then it goes way up from there.
Other questions?
What is the projected lifetime of the Tempo satellite?
The projected lifetime, it should last 10 years, but we're only required to measure for several years under the contract with the satellite producer, and then NASA has in the contract provision for it's extending that 2 years at a time. So a 10-year lifetime would be very nice for us. And it's actually one of my favorite topics now that you mention it, because my hope for the future when I'm sitting on the porch in my rocking chair will be that NOAA will take this up, having proved it with Tempo, and have instruments like this on their future geostationary weather satellites. Because what we're really doing is chemical weather.
So I have a quick question. So would that lead to products available to the public that they could consume and understand?
Yeah, so things like the RSIG I showed from EPA is something, and there are other tools from NASA as well, but they're meant for people to be able to understand and use. And all data from Tempo, from the spectra to the products to the gridded things and all of the stuff we do, is freely available to anyone. Smithsonian cannot deny people access, and we wouldn't want to anyway.
More questions?
Thank you. Great presentation. What I was wondering during the presentation, though, was in our post-fact world, what bearing do you anticipate this will have, if any, on policy decisions that the information should have bearing on?
Let me give you two parts of an answer. We really hope we get past the post-fact world before too much, very longer. And the other thing is that there's been more attention to climate change, to global warming, than air pollution so far. So that they haven't. It's like in the two towers, the eye of the Sauron or whatever he is. They haven't lit on us yet, but our friends at EPA are just taking a real beating. And also, the EPA has been terrible about water pollution and agricultural wastes and pollution. using insecticides that are cancer-causing and especially susceptible to disease in children. So they haven't lit on us yet. I kind of don't think they will. It helps that one of the prominent, very conservative politicians from Oklahoma actually likes this thing, and he likes it because it's a partnership between industry and science.
Questions, yeah?
Well, it's pre-focused. There's no adjustment once we're up there. So the telescope is focused and staked and all set. And if something happens to get it out of focus, then we'd be very unhappy.
Anyone else? Yeah, over here.
You said in agricultural that for like the nitrogen oxide, and you mentioned something of previous studies. Do you know what the previous studies have already shown for the best times to be using fertilizer? Or, because you said that you were hoping to confirm some of the ones.
No, if I said that, I meant this.
Okay.
I don't know what they are, but I did read a newspaper article the other day that said that the months. What's the big cooperative? Land O'Lakes. No, Land O'Lakes is now a big cooperative thing. So we know them for butter, but they do a lot of other things. But they're not a corporation that pays its president $10 million a year. They're a cooperative among different farms, and they're studying these kinds of things. And that was in the article that I saw. Including having a tractor know where to put more fertilizer and where to put less fertilizer and insecticide. Right. Precision farming.
Great. Thanks a lot. Thanks, Kelly.